Welcome to my project bazaar.com. Let me discuss about the project SAR image denoising via clustering based principal component analysis. Let me discuss about the abstract of the project. Image denoising is an important image processing task, both as a process itself and as a component in other processes. Very many ways to denoise an image or a set of data exist. The main properties of a good image denoising model is that it will remove noise while preserving edges. Traditionally, linear models have been used. One common approach is to use a Gaussian filter or equally solving a heat equation with the noisy image as input data. That is a linear second-order PDE model. For some purposes, this kind of denoising is adequate, while some denoising approaches such as a bilateral filter LARC and NLM estimate each pixel separately using other similar neighborhood pixels. Some other recent state-of-the-art page-based methods such as BM3D and Pro denoise a group of similar patches together. These patch-based methods are inherently limited in performance. In our approach, Readme image is added with the medical image. Here, instead of SAR image, we used medical image, and also instead of spectral noise, here we used Bayesian noise. So to make the Bayesian medical image, both clustering and denoising are performed on image patches. Then the despeckling process implemented based on the PCA with LMMC filtering. First, perform the filtering process to resist the influence of noise by reducing the dimensionality. Principal component analysis implemented to reduce dimensionality, and it leads to perform k-means clustering algorithm. For denoising process, LMMC filter denoising model are proposed. Finally, obtain the denoised medical image. In the proposed system, PCA technique to account for Bayesian noise. Here, instead of using block matching approach, used clustering approach. In this proposed, use the combination of log transformation, PCA and k-means methods for finding similar patches. Initially, convert the image into patches, log transformation performed, and then convert to PCA domain. Then applying LMC filter to processing the denoise process and perform the inverse transformation. Principal component analysis, that is PCA, is a statistical procedure that uses an orthogonal transformation to convert a set of observation of possibility correlated variables into a set of values of linearly uncorrelated variables called principal components. The LMC filter is a filter used to produce an estimate of desired or target random processes by linear time invariant filtering of an observed noisy process, assuming known stationary signal and noise spectra and additive noise. We discuss about the flow diagram for our process. Here, input image are captured from the dataset folder. Here, we capture the medical image as an input image. In the noise image stage, an image is corrupted by Bayesian image. One goal in image restoration is to remove the Bayesian image from the medical image in such a way that the original image is discernible. Bayesian image, the apparent reproduction of an object formed by a lens or mirror system from refracted or diffracted light waves. Next, in the dimensionality reduction, where log transformation and PCA domain are proposed. Some variables are not normally distributed and therefore do not meet the assumption of parametric statistical test. Using parametric statistical test on such data may give misleading results. In some cases, transforming the data will make it fit the assumption better. Many variables in biology have log normal distribution, meaning that after log transformation, the values are normally distributed. If the data shows outliers at the high end, a logarithmic transformation can sometimes help. The logarithm function to piece together the larger values in your data set and stretches out the smaller values. The following illustration shows the histogram of log transformation distribution. When you select logarithmic transformation, compute the base 10 logarithm of each data value and then analyze the resulting data. Next, in the PCA domain, that is principal component analysis. PCA is the simplest of the true eigenvector based multivariate analysis. Often its operation can be thought of as revealing the internal structure of the data in a way that best explains the variance in the data. If a multivariate data set is visualized as a set of coordinates in a high dimensional data space, PCA can supply the user with a lower dimensional pictures, a projection or shadow of this object when viewed from its most informative viewpoint. This is done by using only the first few principal components so that the dimensionality of the transformed data is reduced. PC is closely related to factor analysis. Factor analysis typically incorporates more domain-specific assumption about the underlying structure and solves eigenvectors of a slightly different matrix. TC is also related to canonical correlation analysis, that is CCA. CCA defines coordinate systems that optimally describe the cross covariance between two datasets, while PCA defines a new orthogonal coordinate system that optimally describes variance in a single dataset. Such dimensional reduction can be very useful step for visualizing and processing high dimensional datasets. Next, in the denoising process, we need to cluster our PCA features by using the K-means algorithm. So the K-means clustering is a method of vector quantization originally from signal processing that is a popular for cluster analysis. In data mining, K-means clustering aims to partition an observation into K cluster in which each observation belongs to the cluster with the nearest mean, serving as a prototype of the cluster. This results in a partitioning of the data space into organized cells. The problem is computationally difficult. However, that there are many efficient heuristic algorithms are proposed. These are usually similar to the expectation maximization algorithm for mixtures of Gaussian distribution via an iterative refinement approach employed by both algorithms. Additionally, they both use cluster centers to model the data. However, K-means clustering tends to find clusters of comparable spatial extents. Next, the cluster result are passed to the filtering in order to remove the Bayesian noise from the medical image. Here, LMMC filter are proposed. Linear minimum mean square error filter are proposed. Here, the LMMC estimate an ideal image, that is where the medical image and also the noisy means are combined. These images are filtered out using the LMMC filter. Finally, we obtain the result. Let me discuss about the abstract of the project. Select the main template in the current folder, right-click the pen and run for executing this process. This is the main window of the denoise the medical image using principal component analysis based LMMC denoising. By pressing the input image button, we can browse the input image from the dataset folder. Select any one images from the dataset folder. Here, I display the input image and convert if our input image having 3 band. Then we need to convert our input image into single band, that is gray conversion. By pressing the noise image button, we created the noise image with the Bayesian distribution of noise. Here I display the noise image in the access toolbar. By pressing the log transformation button, we can transform our input image into reduced dimension by using the logarithmic transformation. Here I display the initial value of PSNR level. This is the log transformation result. Here I display the log transformation result for our entire image. Here I split the log transformation into segmented result. Here the noise level for every segmented region. By pressing the sub-images button, we segment our noise image into segmented sub-regions. By pressing the PCA button domain, we can extract the principal component features. Here I display the PCA images for every segmented region, and this is for every single segmented region, and this is the PCA features. Here I displayed in a table format. By pressing the feature extraction button, we can extract the features based on the PCA. Here it displays the feature extraction values. By pressing the K-means algorithm, we perform the clustering of our feature extraction values. Here display the clustered group. By pressing the denoise patch, we perform the LMMC filter operation. This process will take some time for executing. Here we obtain the denoised image. And here I display the final PSNR value for our denoised result. Finally, the medical image are denoised effectively with the PCA domain based LMMC filter approach. Thank you.